and come back here. Start the present. Okay. And hopefully, presenter view.
Yeah.
Beautiful. All right. Okay. Hi, I'm Cornelius. I'm an engineer. I work on the first floor. I'm Dan Vigneron's lab. I've been doing Dissolution DNP for a few years now. In this part of this class, we're basically going to talk about very practically about how we do Dissolution DNP. Specifically, really on the Hypersense system is what I'm going to talk about because that system is substantially easier to operate from start to finish, and that's probably the one that most of you guys will be using, at least for your initial work. As you guys know, this is a system that's designed for preclinical work only. But first, we'll maybe just talk a little bit about the basic method of Dissolution DNP, and for that, I urge you to check out, in particular, the original paper of Jan Henrik Arden-Carl-Larsen from 2003 in PNAS, which is probably on the course website. If not, I'll upload it there. And there's also a very helpful operator manual for the Hypersense, which we'll be sure to post up there as well if it's not already. And so everybody, yeah, feel free to just jump in, and if you have comments or questions or whatever, there's probably a couple people in here that have more experience than me on the Dissolution DNP. So feel free to chime in. Okay, so first, you've all seen the Hypersense now from the labs over the past 2 weeks. Here's a few basic things to know about it. Number one, it's quite a robust system as long as you follow the procedures that are prescribed and you keep very good documentation of what you're doing. So in particular, you want to keep track of the status of whether there's a sample loaded or not in the system because the system does not have an intrinsic sensor for that. You have to specify that to the system. So that can lead you to some difficulty if you get into a situation where you don't know. So we'll talk about it a little bit more soon. And as Peter has described over the past couple of weeks, this is essentially a modified NMR spectrometer. So this particular one was a 7T originally NMR spectrometer that they've instead ramped to 3.35T. And then there's basically 3 additional key modifications. Number one is that this system has been modified to allow the bore of the NMR magnet to reach a very low temperature. And that's to facilitate the DNP process. So we get the polarization of electrons at that temperature. And then, of course, we have the addition of the microwave system to transfer polarization from those electrons to the carbon-13 nuclei. And then third, we have this dissolution system, which was really the key breakthrough in Dissolution DNP, which has enabled us to get liquid state samples. And so I'll just point out, maybe kind of obvious, but maybe if you hadn't thought about it, maybe it's not obvious. The inside is kept cryogenically cold for 2 different reasons. One is the actual magnet windings are kept cold to facilitate superconduction, so we get a 3T or more magnetic field inside this NMR system. But then also we need those cryogens to actually cool down the actual inside, the bore of the magnet itself, so this is something that's different from a normal NMR system. And so a theme that will be recurring here about this particular part of this class is ways to not mess things up and not break the system and not, believe me, you do not want to get Mark VC upset with you because he has a long memory with these things. Yeah, short temper, long memory. Yeah, you just don't want to. You want to keep an eye on, in particular, there's a few things you want to do. Keep an eye on the cryogen levels. So basically, a rule of thumb here is you want to keep the liquid helium level above 25% or so, liquid nitrogen level above 40% or so, and you definitely want to conserve cryogens and ensure that they're being refilled. To actually conserve that, you want to idle the system whenever it's not in use, and basically minimize the time that the VTI insert, which I'll talk about in a minute, is open. Because those are basically those are both situations where you're ending up, in particular, losing helium. And so this cryostat that I referred to holds about 85 liters of liquid helium and 71 liters of liquid nitrogen. And the helium is particularly an issue because these days there's you guys may know there's this global shortage of helium. So it's quite expensive at the moment, probably is likely to remain so for a while. So I'm not sure exactly what we're paying for helium, but estimated it was a few $1,000s worth of helium in here at a time. And the nitrogen is probably only $100 or $200 worth. But you want to keep you want to keep keep an eye on these levels, and most importantly, you want to avoid a quench situation, which I don't think we've had that happen on any of our polarizers, but that could be pretty bad. So keep an eye on this stuff. And so you get an idea of how much the levels, like how much is used per study or day. The system will use approximately like up to 10% of the liquid liquid nitrogen per day, and about 1% of the liquid helium per study. So just something to be aware of. So and then the other key thing that we want to talk about before we get into anything else is safety. And like pretty much all the practical NMR or MRI systems out there, they're not using electromagnets for the main field, or not resistive electromagnets. They're either superconducting magnets or permanent magnets, and these systems are always on. So this main magnetic field is always on, and this is potentially a hazard for multiple reasons. So you just want to be careful around these magnets. This, of course, is less of an issue than it is for a clinical MRI scanner, where there's a much larger fringe field. But you still don't want to bring ferromagnetic materials near the bore, and you don't want to. It's just good practice in general not to bring, to be aware of these fields, and not also bring people with pacemakers in the vicinity of these high magnetic fields. Another safety issue, which I've seen can be problematic, is you want to be careful when you're up on ladders, loading up dissolution media into the hypersense in particular. You've got to climb up and reach the bomb part at the top, which we'll talk about the anatomy in a minute. But as another thing to be aware of, another thing is heat. So the big bomb up there is it's going to get up to a very high temperature, 200 degrees C, high pressure. You don't want to really mess with that too much. You don't want to touch any of the metal stuff up there at the top of the hypersense. And as I mentioned, be aware of cryogens. If there is a situation where there was a quench, then I mentioned about 100 liters of helium and 100 liters of nitrogen. That would turn into about 800 times that and get released into the room. These systems aren't vented, so it would be, you probably want to get out of there if there's if all that gas is released. It's not really that much, I don't think, but still, it's something to be aware of. And then another key thing actually is you need to be aware of any possible chemical reactions that you may be creating. So if you're dissolving a sample, if you had, I could conceive of a situation where if you loaded a sample and then you had like an extremely acidic sample and extremely basic dissolution media, and then you dissolve that, mix those, you could have a situation where you could result in some explosion potentially. I mean, it's not likely, but you want to be, you need to be really aware of everything that you're doing on these systems. Okay, so let's get into a little bit of detail on the hardware here. So this is a figure from the first paper by Jan Henrik et al. And it shows how this is really a modified NMR. Does this thing have a laser on it? Oh, here's one. Okay, great. So yeah, it's a modified NMR spectrometer. We can go down the list of the parts here. Okay, so number one, DNP polarizer. Okay, that's not really very helpful. This is this whole thing. Okay, number one. Uh, so the real critical part, I think, is this VTI, which is part 3, which is this insert that sits inside the bore of the bore of the magnet, and this is the part which forms this sealed enclosure in here inside the magnet, which lets the bore of the system reach very low temperature, and it does this by filling this insert with liquid helium. So this insert will be, when the system is cooled down, it will be filled mostly with liquid helium, and it will also be depressurized by this vacuum pump that sits outside the system, like right next to it. So this number 2 here is this vacuum pump that depressurizes the VTI. This VTI is also filling up with liquid helium, which comes from the same reservoir that is, I believe, the same reservoir that's keeping the superconducting windings of the magnet, which I think are in here, keeping that cold. So that's really probably the key modification. But then, of course, there's also several other modifications. There's the microwave source here, number 4, which sits, this is a zoom in of this area here at the top of the VTI. And so this is a microwave source that's introducing microwaves into this bore cavity here and irradiating it and allowing the transfer of polarization. Let's see, what else we got here. The dissolution system is partially shown here. So the bomb that sits up above everything is not shown here, but that's where you'd put your solvent in, and that would get heated up, and then it would shoot down into the sample when you're ready to dissolve it, and that occurs through this what's called the dissolution wand or dissolution stick, and this is what links the DNP system to the dissolution system. And so if you look here, there's 2 tubes that come, there's one, so there's 2 tubes. There's one that brings the heated solution down from the bomb and then into the sample cup. And then there's another tube that takes the dissolved sample out, and then that will go out through a tube, and then you can collect that liquid state polarized sample and then bring it to your living system of interest and do your hyperpolarized experiment. Couple interesting things about this. The microwave system is like 90 gigahertz for a 3.35 T magnet, like the Hypersense, and it's a fairly obscure range of microwaves. There's not really like a lot of practical stuff that operates in this range, so the sources are pretty obscure. Like basically, this is like it's called the W band of microwaves. It's something like what you might use if you were going to build a Death Star or something. Like you wouldn't really like ever use this for something like practical. Like even radar and stuff is lower in general frequency than this. So just sort of interesting because it's basically restricted to like military applications. So I think some of these sources they actually got from Russia, or I don't know, Dan might know where. These are Russian like sources, or some.
Nicaragua.
Oh, okay, great, yeah, awesome, yeah. We traded several hostages, I think, for this. Or
Now they can make them out of diodes.
Oh, okay.
Diode in the last 5 years
Okay.
for these powers.
Okay, oh, it's pretty low power, I guess, right? Yeah, I see. Yeah. Okay. Well, so they've read about some systems that they use for like crowd control. They can like actually like shoot like 90 gigahertz radiation out of people, and it like heats up their skin, and but this isn't that kind of power. So, okay, so let's talk about. So we talked about like the innards of basically the DNP apparatus. Let's focus a little bit on the dissolution part. So the pressure chamber, which you've all seen, and I think probably you guys have seen this all over the past couple of weeks when you've gone, in the lab and seen it. But it's helpful to really talk about it explicitly. I think up here there's this the pressure chamber, or also known as the bomb. It's the bomb, yo. So up here, this is where you load your. No laugh, really? Okay. All right. Up here, you load your solvent in here. Close this valve here, and your solvent gets pressurized up here to this superheated condition where it's about 200 degrees Celsius and 10 bars, or about 10 times atmospheric pressure. So this is under quite high pressure and temperature. So if you think about it, it's the exact opposite of what's going on with the sample that's down in the DNP apparatus. That's going to very low temperature and very low pressure. And up here you've got your solution that's at very high temperature and very high pressure, right? So because you've got to cancel that out basically to get to a liquid state sample that you can inject into a living system. So this will take a couple minutes to reach that temperature. And so as I mentioned, you don't want to touch up here. It's going to be pretty hot, and there's some warning signs up here. So basically this will shoot down through one of those tubes in the dissolution wand, and then come out, and it'll go into your flask, and yeah, you get your solution out. So let me emphasize again, the only thing up here you want to touch is this green valve that's up there that will open and close the bomb. And this horizontal position is the closed position, just so you know. There's a couple of the critical accessories that sit right by the Hypersense. There's the big vacuum pump. It may or may not look exactly. I think the ones that we have downstairs look a little bit different than this, but it's this big metal thing that's going to sit right by the polarizer. And in the schematic earlier, you saw how this is basically keeping the VTI depressurized. And so this is also responsible for most of the noise that you hear when the system is in operation, when it's in the non-idle status, so when it's on. And there's also this helium push gas, which you need to keep an eye on as well. You want to make sure that you've got sufficient helium gas pressure here. So this pressure is used for pushing the dissolution solvent very quickly out of the bomb that sits above the polarizer and down into the sample, and so you can really rapidly dissolve your sample. So I think it's also the gas that's used for pressurizing the bomb. I could be wrong, but and maybe even doing some pneumatics in the system. I'm not really sure exactly, but you want to make sure that you've got this pressure because you do need it for the dissolution. Okay, so I'll take you through maybe a little bit about the software now too, just so we get.
The bomb has to be filled with helium gas.
Okay, yeah, that's what I thought. Oh, okay, yeah, that's a good point. Yeah, right. Okay, so that makes perfect sense. So, yeah, you couldn't use just regular air in there. You have to use helium gas for that. So you pressurize the bomb with that same helium tank. So we'll go through a basic polarization procedure here from the software. So this is a very highly practical kind of part of this class, but I think it's worth just showing you the software one time. So basically, when you walk up to the Hypersense, it's more or less going to look like this. And I'll highlight up here, there's an indicator that says sample missing or sample present. However, this is not based on any actual sensor. This is based on whether you tell it, whether the last person has been responsible and said, that they actually inserted a sample, or, basically it's up to you to notify the system when you load or unload a sample. And so this is a good thing to check, but ultimately you also want to check the documentation. So every polarizer has some a sheet of paper or a book, logbook. It's been standardized now, I think, for the polarizers. There's like a logbook that has pages of entries where you put down the date, time, and what you've done with the system, what you loaded, and so hopefully there should never really be a problem with ambiguity about whether there's a sample loaded, but there has been some issues with that in the past that resulted in, for example, the dissolution solvent being shot into an empty bore, which is not a good thing to have to deal with. So okay, so yeah, so again, so this is a significant vulnerability of the system that we want to highlight and make sure that we're paying attention to. So assuming the system's available and assuming that the sample is missing, we can go ahead and the first thing you would do is hit this cool down button. And so this will initiate the depressurization of the VTI, which you can read the stats on the VTI here. It shows you the, or it's also known as a DNP insert. It shows you the temperature inside there, the pressure, gives you information about the microwave system that's not on yet. But basically, you're going to press the cool down button, and you're going to watch this temperature drop, this pressure drop, and this liquid helium level rise. And eventually, it should drop to around 1.3 Kelvin. And this liquid helium is designed, what's the typical setting is to let this rise to about 65%. Okay, so if you open the door of the Hypersense and look inside, which you've probably done the past couple weeks, this is roughly what it looks like. So this is this stick here. This is the dissolution stick that we mentioned. So this has the tubes that go in and out to carry the solvent down and then carry it out to the sample. Of course, here's the bore and the big magnet here, and this is down here is where the DNP process is happening. So this is currently in a non-operational state. You see this dissolution stick is over to the side. It rests on this spring-loaded collar here so that you can get access to the VTI. So this is ready to be, it's ready to sort of load the sample in here. So when you click Insert Sample on the main, well, I'm skipping ahead here. Let's go back here to this screen. So after we've hit cool down and this level's coming up, while it's cooling down, it's a good time to take out this other stick, which is the loading stick. And this is where we actually take our Hypersense sample cup, and which we've loaded with our mixture, which has our C13 labeled agent, our radical, and maybe some gadolinium, as we talked about. And we load this onto this sample stick apparatus. And we're going to take this and then load it on there, and then we're going to do insert sample, which is that button, this insert sample button on the interface. And it's always going to be a normal sample that you want to insert. You don't ever want to do this solid state probe sample. This will result in serious failure of the Hypersense. And so you'll get this, it'll take a minute for the VTI to open, and then you'll be prompted to go ahead and insert your sample. And so you'll reach in there and put this loading stick down into the VTI, which will now be open. And this stick is has two concentric cylinders, which you can use to load the stick and then dislodge the stick by pulling up on this inner rod, which will then displace this stick from the end of the displace this cup from the end of the loading stick. So you just shove down and then pull up on this inner ring, and this will dislodge the sample cup. And people who are going to use the Hypersense should practice that procedure if you haven't already in the lab. So then once you've loaded the sample, you can go ahead and move this dissolution wand or dissolution stick over into the operational position. And so now we have this solvent system is now hooked up with the DNP system. So now it's basically ready to dissolve, at least once you've built up your polarization. And you'll get this critical screen here where you need to confirm that, in fact, the sample has been inserted correctly. So this is where the system makes a determination that a sample has, in fact, been loaded. And it's important that you check your loading stick to make sure that the sample cup is not still on the loading stick. Like sometimes people have thought that they loaded a sample, but it turned out there was actually still on the end of the loading stick. And they proceeded through the screen with this box still checked, and so they thought they had a sample loaded, when in fact there wasn't a sample loaded. So you really want to check to make sure that you've gotten the cup into the Hypersense, and only in that case would this box be checked, and that would be the typical case. But you just always want to check that. And when you click Finish now, the interface will say that now that you have a sample loaded, and you can go ahead and start doing your polarization. So the very next thing you would do is load your Polarimeter software, which is a little NMR measurement of the polarization buildup of the C13. The inside of the VTI also has a little C13 NMR coil, which monitors buildup of the C13 polarization. And so you start this software and run solid buildup. And so this will monitor buildup of polarization. And so then the last thing you have to do is now turn on the microwaves. And so that you do by pressing this polarized sample button, which is grayed out here. But if you had actually loaded a sample, so this still says sample missing, but if there's a sample in there, this polarized sample button will be black, and you press this, and at that point you can dial in your microwave frequency, which presumably you've determined previously by running a microwave sweep where you test several microwave frequencies. And you choose your microwave power, although I think we pretty much always use 20 to 25 milliwatts for this. And we can choose the sampling time for monitoring the buildup of the polarization. Like a typical number would be like every 5 minutes or 300 seconds here. And that's really it. So at that point, you'd run your, you'd walk away and let this polarization build up. And if you've ideally like made a prep like that, like say for pyruvate, if things are working right, you might have a buildup constant of like half an hour or something, so that in basically in an hour you've built up close to 90% of your polarization. So you get a screen that might look something like this. The software will track the buildup of your polarization. So for example, could somebody maybe estimate the buildup constant here from this curve? Somebody want to take a shot at that? Like, let's assume this axis here is in seconds, and this is the polarization. I'm actually not sure of the number. I'm not sure of the number here myself. Oh, you converted it into minutes? Wow, that's impressive. How many seconds? I have no idea. Okay, so let's just say maybe it's building up to like 3,000, maybe a little less. No, maybe let's say 3,000 is the max value. So then what's, let's just say 90% is 2 T1s. Like that's,
like 900,
so yeah, so if we drop, yeah, I think that's probably pretty close, yeah. So if we drop like 10% from the maximum value, like which would be around 3,000, we come to 2,700. Let's say this is 2 buildup constants. This is just approximate, right? But let's say that's 2 buildup constants. So if we're at 20, let's call that 2,200. This could be, there could be a substantial error here, but the idea is to try to get this, like, you know, get the right order of magnitude for these buildup constants and be able to, you know, look at these curves. And it'll display a fit on the screen, but it's good to just, you know, be able to see this pretty quickly. So, like, you know, if this is 2,200, so half of that is 1,100 seconds. So what's that in minutes? What did you say earlier? 20 minutes, something like on that order of 20 minutes. So that's pretty good. That's like, you know, as long as you're not way off or something with your prep. So it's important to keep track of this, because if you've got a really short buildup constant, you're probably giving up something in terms of polarization, or if you've got a really long buildup constant, then that may not be practical also. So.
so do you want to be at that 100%, or do you
Well, so you want to be, I mean, personally, I think you want to be at like 90%, because that's like, you know, what you can do in like the 2 buildup constants. But everything depends on, you know, like, I don't know. So it depends like on a lot of factors, like what your exact prep is. I mean, how much time you have to polarize, you know, but there's like diminishing returns, right? If you have a really long.
I guess I was just wondering what the definition of a buildup constant would be. Is that like just like 50% of?
Oh, no, it would be, so, oh, right. So it would be like 1 over, so it's basically the time that it takes to reach 1 over, let's see, should be able to, 1 minus 1 over E, yes. So
Yeah.
the constant is the time it takes to reach 1 minus 1 over e, which is, I think, approximately 60, I'm going to go with Jeremy on that one, 63% of your maximum polarization. And so if you go another 1 minus 1 over e of the remaining 27%, then you get some number, I think that's like 80 something, high 80s, like maybe 87 or something. Marker doesn't work. But that's that 90% that I was referring to after two build-up constants. It's just kind of a rule of thumb. You could, do this however you want to, but usually you're in good shape if you've got 2 build-up constants worth of polarization. Okay, so at that point, it'll be time to click, once you've, let's say, built up for 2 time constants, it'll be time to go ahead and click Run Dissolution. So that's this button here. So you're going to get your solvent out, whatever that might be. Typically, like it's going to be some kind of aqueous solution, probably not methanol. I'm not really sure what experiment they were running here, but so you'll pick a dissolution method, which will just be specify the pressure and temperature that the solvent will get up to. But there's a standard typical one, which is the 200 C and 10 bars, which you'll most often choose, which is probably going to be related, or it's going to be called pyruvate. So at that point, you're going to do next, and then you'll be prompted to load your solvent up into this top, the bomb here, up here. So you'll open that valve and then go ahead and load that solvent into this bomb. Then close the valve and click Finished. And at that point, the bomb will pressurize. And so this number here that you see, I believe, is the pressure in the bomb in atmospheres. And it will go up to the maximum. And once it's reached the maximum, the dissolution process will be triggered. And you'll get the hot liquid shot down into the sample. So the sample will be raised up partially out of the magnet and then dissolved there, and the liquid sample will be moved to your output tube and into the flask. So that's basically it. You have to do a little cleaning after you're done. So I'm skipping your experiment, which is like a whole other thing, but that'll be talked about I think in the future lectures in this class. But once you're done here, you're going to go ahead and do the cleaning, and basically we ask that you run a few milliliters of water and EDTA mixture. EDTA is a chelating agent that will chelate any metal ions that might be in the system, which we don't really want, and just do that process twice, and then we'll run some air through the system as well. Basically, we don't want anything in the dissolution system gunking it up, and so just run this cleaning process after every single dissolution. So I think that's pretty good summary of the operation of the Hypersense. I don't think we need to do microwave sweep, discuss that. We can talk about that in the lab maybe. Let's see. Yeah, there's a few other things to be aware of, errors that you can run into. So this will be covered a little bit more in the lab, I think, today. Is Mark VC running or is he kind of like doing stuff? So he'll be demoing some possible failure modes, I guess, of what situations you can run into on the system. So I'll leave that to him. So just one last thing, I guess, is be aware of this sort of routine maintenance that's required: cryogen fills, changing the helium gas tanks, cleaning the dissolution system. That's actually after every single dissolution. And then doing a bake out every once in a while is important. You'll find that after you've loaded like 50 samples or so, that the minimum temperature that the system can reach starts creeping up. And it's due to some accumulation of material inside the variable temperature insert. And so every once in a while you have to heat it up, and this will help get rid of some of that material that shouldn't be in there. So yeah, that's it. Should we move to the lab at this point, or yeah, please?
So for the actual vacuum part, how exactly does that cool from 4K to 1K? Is it like just ideal gas law, or like the change of liquid to gas?
Yeah, so that's a good question. So as I mentioned, the bore is filling up with liquid helium, which I think is sort of kind of maintaining a temperature that in the liquid state of, I think, which is like it's 4 Kelvin. Okay, so
Yeah.
okay, so then, yeah, I guess the additional depressurization, it must be what lowers the temperature. I guess, yeah, I guess something like ideal gas situation. I'm not sure actually.
Yeah.
Yeah.
Because Dave and I were also talking, we were thinking it's because since there's no more gas molecules, like some of the liquid helium could burn to gas, and that requires a temperature to like go over the activation reaction.
The heat that's in the liquid helium is like getting removed as it evaporates.
Yeah.
And that's lowering it from 4 to 1.
4 to 1. So does it mean over time it'll re-equilibrate back to 4 Kelvin?
Not if
For
you
at least.
keep it at the lower pressure.
Okay.
So you do depressurize them right before you dissolve it.
Yeah.
During that time, that's why you want it quick, because the temperature goes up. T1 gets shorter and your polarization will go up. The spin lab is different in that it's at a different, it's at a vacuum. So it's always at less than 1 Kelvin even during when dissolution starts.
That's because the sample like lifts out, right? Or something.
Right, because you're not opening it up. Yeah, so it's all sealed. It's in its own environment. You do lift it out of the gas, just out of the helium level, so you don't boil off helium that way. But it's still a vacuum. It's still at 1 degree Kelvin until the hot water hits it. But in this, it's you depressurize. The temperature starts rising before the hot water comes in.
Anything else?
All right. Great. Yeah. So